Mhm. All right, welcome to the Aurorasaurus Ambassador call for July. We are excited to have two special guests here today, and many of you all ambassadors from around the world here with us, around the world and Washington State. It's all great. I will introduce our two main speakers, and then Laura, you can help me with anything I forget. And after that, we'll hear from each of them for about 10 minutes and have some more questions, time for questions, and time for any updates on what you all have been up to with Auroras or presentations or noctilucent clouds or whatever it is. We're excited to hear about that as well. But first, we're very excited to have two speakers today whose work has been featured by NPR and Science Friday, following on to papers about Aurora. And Jim will be telling us more about that. He is an experimental plasma physicist and assistant professor at Wheaton College in Illinois. And he studies waves in plasma, both in the those that can be kind of generated from artificial plasma sources on Earth, like that he can tell us about, as well as how that looks in the natural environment as well. Such as Alphanic Aurora, and you have many experts here who I think have seen a lot of Aurora and captured it and are keen to talk about that as well, those examples as well. So I'm excited to meet you. I don't think we've met, though we know people in common for sure. And then also we have Laura Hollister from California, where she's been an earth and environmental science educator for going on 20 years. She's passionate about using place-based and inquiry-style teaching to help students develop an understanding of the process of science, their own ability to do science, and its relevance to their lives. She has a bachelor's in geology and a master's in environmental geology, and is past president of the National Association of Geoscience Teachers, Teacher Education Division, which is great. And she created some very cool educational resources about the topic that Jim will be talking about, and which is also diffuse and discrete aurora. So I'm not sure how you guys got together on this project, but we will be excited to hear more about that. Laura, do you want to add anything else that I've forgotten about here?
No, I think we're good. I'm looking forward to hearing more from Jim and Laura.
Yeah, we're definitely interested both in the science and the education and the connection to Aurora as well. So please take it away, Jim, if you want to start.
Yeah, happy to. Yeah. All right, let me share a screen. I think you should be able to see my PowerPoint now. Yeah, my name is Jim Schroeder. I'm an assistant professor at Wheaton College outside of Chicago. Wheaton is a suburb of Chicago. And I'm joined today with Laura. We got connected by Science Friday, actually. They reached out to us and had us combine my experience in research with Laura's experience in education and come up with an educational resource that you'll hear about. And my goal with this presentation is to try to set up the resources as much as I can. You'll see I am using slides that we actually created with Science Friday, and so you'll see that icon down there. So I'm doing a little bit of recycling here today with the PowerPoint that you'll see. All right, so when I'm talking about auroras, one of the things I like to do is sometimes just show people pictures and ask them what questions they have. And so here's a couple pictures that I might show if I was trying to just get the conversation going, and I'd ask people what they notice or what comparisons. And of course, there's really a shocking difference between these pictures. There's a number of shocking differences. I'm going to kind of guide this a little bit for the sake of getting towards my research and say one of the questions that often comes up is what causes auroras? And I'm guessing quite a few people here are familiar with this idea. Auroras are caused by electrons that come raining down from space. And so that's shown schematically here as kind of pink raindrops coming down from space and crashing into the atmosphere, giving their energy to atoms and electrons in the atmosphere. And then eventually those atoms and molecules relax down to a lower energy level and give off a flash of light, a photon. So when a bunch of photons are given off across the sky, that's what we see as an aurora. So another question is, where do those electrons come from? And now, as an experimental plasma physicist, I need to make sure I use the word plasma as much as possible. They come from plasma that's out in space. Sometimes this is just called hot ionized gas out in space, but we like to try to get the word plasma in there. And actually with the James Webb pictures coming out this week, we were trying to figure out how to get people from NASA to say plasma more often instead of just hot ionized gas. But the idea is that space, and particularly the bubble of space around the Earth, is filled with plasma. So Earth has this kind of region of magnetic influence called the magnetosphere. And this is where Earth's magnetic field is the main magnetic presence. And this region of space is filled up with plasma from the sun. But let's back up for a second. Plasma is a state of matter. So if you take a solid like an ice cube and heat it up, you get liquid. And if you continue heating, you have another phase transition to produce gas. And if you continue heating beyond that, you get ions and electrons. So what happens is that the individual atoms of the gas have enough energy once they get hot enough to actually break apart. So the electrons can float around freely and the ions can float around freely. And that's plasma. It's this gas of ions and electrons. And so that is what's out in space around the Earth. And that's where the electrons come from. Now, one thing that might pop into people's mind as they're looking at those pictures before is the striking differences in the appearance. For lack of better words, at least to start, maybe people would say that they're hazy and streaky is one main difference here. Now, if you're in the world of auroras, you probably know that those are called discrete and diffuse auroras. So discrete auroras have these well-defined bands of light. They can kind of wiggle and writhe around. And diffuse auroras are more featureless and kind of hazy in the sky. So here's a time-lapse video of discrete auroras. And one of the things you see here is kind of the ripples that move along these arcs and the waviness and the periodicity. So here's my super scientific word to describe this. Notice that these things are kind of wavy. And that begs the follow-up question that people have been asking for a long time. Are waves a part of explaining electron precipitation? And so are the variations of waves out in space actually imprinting some features onto the auroral displays that we see here? So to start answering that question, I'm going to compare data from two satellites. At higher altitude, it is a satellite called Polar. It's in a polar orbit, so aptly named. And then further down at lower altitude is the FAST satellite, the Fast Auroral Snapshot Explorer. And these two satellites were strategically placed to bookend a region of space called the Auroral Acceleration region, or AAR is what I'll call it on the coming slides. And what'll happen here is with Polar further out or at higher altitude, we'll be able to see what's flowing into this kind of funnel-shaped region in space. And with FAST down at lower altitude, we'll be able to see what's coming out the bottom end of this funnel-shaped region of space. So first, let's take a look at Polar data. Polar tells us that Alfvén waves, a type of electromagnetic wave that exists in plasmas, Alfvén waves are really common above auroras. And here's how Polar data was used to answer that question. So here's a single ultraviolet picture of auroras. This picture was taken above one of Earth's magnetic poles. And so the magnetic pole is here in the middle. And so that means that the sun the day side of the Earth, the half of the Earth that's illuminated is towards the top, and the night side of the Earth is towards the bottom of this image. So that's one snapshot. Thousands of snapshots were combined from polar into this image. And so this is a composite intensity map. The coordinates here are referenced to the sun. So noon or 12 here is always pointing towards the sun, and the Earth rotates underneath. And midnight is always pointing away from the sun. And then there's some latitude numbers here as well. That's reference to where a magnetic field line from the Earth actually strikes the Earth's surface. So this band of auroral light is also on average present as well. It's statistically present. And what Polar was doing while it was taking these snapshots was also measuring the electromagnetic waves that were traveling down towards Earth. And this is where the Alfvén waves were found. So Alfvén waves were found flying past Polar, going down towards Earth. And if they were mapped down to a coordinate system, the same coordinate system, looking at the sky, we'd find that those Alfvén waves coming down past Polar, down towards Earth, actually map to the same regions of the sky where auroras are found. And so this is a striking kind of similarity, thinking, hey goodness, there's auroral light being given off in these regions of the sky, and there's Alfvén waves above auroras in the same region of the sky. So let's do a quick comparison of polar and fast. Remember, polar is up at higher altitude, fast is down at lower altitude. And what's flowing into this region on average during times where auroras are active, during storms and substorms, polar is finding on average about 6 gigawatts of Alfvén wave power flowing into this auroral acceleration region. And then coming out the bottom is less than half of that. Less than 3 gigawatts were coming out the bottom of the auroral acceleration region. So this begs the question, where does that energy difference go? And does it possibly go into electrons, actually pushing electrons down towards Earth? So we can't mention gigawatts without thinking about Back to the Future. And so we've got more than 1.21 gigawatts here of power that we're thinking about. We're thinking about multiple gigawatts, which is a lot of power. So this has led to a hypothesis that was actually in the data or in the literature for over 40 years without being directly tested, that perhaps Alfvén waves are a part of pushing electrons towards the Earth to cause auroras. So here's an animation of how this process is thought to unfold. Alfvén waves are created, these electromagnetic waves are created further out in the magnetosphere. They travel down along the magnetic field towards Earth. And then somewhere in here, the magic happens and they start pushing electrons down towards Earth to cause auroras. And on the right-hand side is just a still image kind of depicting this same process as well. Alfvén waves coming down towards Earth, and then eventually starting to push electrons. And that's the hypothesis that was around for 40 years or more. So we decided to go to the lab.
Can I interrupt you for just 1 second?
Yeah,
there's
absolutely.
A good question in the chat about if you could specify where this auroral acceleration region is. I think you kind of had it on like 2 slides ago, but just it's along the field lines, but also, is it really straight up like that? Do we know?
Yeah, so I'll take a shot at answering this. There might be people on the call that actually know better than I do. But the auroral acceleration region is between about 1 and 3 Earth radii above Earth's surface. And it tends to be kind of a cone-shaped region above the auroras. So following out on magnetic field lines, kind of flaring out in kind of a trumpet shape, like the bell of a trumpet, and between about 1 and 3 Earth radii. Right. So that's where electrons start moving earthward that are associated with these discrete auroras. Of course, there's diffuse auroras, and those may be coming from the radiation belts and other wave particle interactions elsewhere. But this is one region where electrons start to be accelerated earthward.
Yes,
Is that,
definitely. So like in the cartoon, it's probably more of a 3D thing than what's
that's right.
sort of shown, but
That's right.
yeah, that's great. It's above Aurora on the field lines. Could you tackle this question about what makes an Alfvén wave different than a radio wave or a sound wave or a water surface wave or a
Yeah.
rope? Some
So
crazy magnetohydrodynamic combination of all those things.
that's right. So yeah, we're used to thinking about light waves or X-rays or radio waves. But in plasmas, there are additional kind of types of vibrations because the particles that make up the plasma actually respond to electromagnetic fields. And so there can be more kind of pushing and pulling between the particles and electromagnetic fields that open up new types of vibrations. So the way that I describe Alfvén waves to people is if you imagine plucking a string, and this is a really common description, I didn't come up with this. If you imagine plucking a string, what happens is that waves will travel down the string. And so in plasmas, something similar can happen, except instead of plucking a string, you pluck a magnetic field line. So imagine taking a magnetic field line and somehow disturbing it. And of course, there's all sorts of disturbances of Earth's magnetic field from the solar wind. But if you take a magnetic field line and disturb it, then the disturbance can travel along that magnetic field line, a similar picture to waves traveling along a string. And that has to do actually with the interaction of magnetic energy being stored and the contortions of the magnetic field line, and then that provides some preference for restoring or straightening out the magnetic field lines, and the inertia of the plasma particles themselves that interact. So in general, whenever you have waves, there's some sort of restoring force and some sort of inertia. And so in plasmas, there's restoring force and inertia from the magnetic field and the plasma particles themselves. Any other questions in the chat that I was missing?
No, I think that's most of them.
Okay. Yeah, so there's kind of a whole zoo of plasma waves. Yeah, the entire textbooks given to just the concepts of waves. Okay, so what we did is turn to the laboratory, because the idea here is it's actually there's a detailed process that is believed to be unfolding in this region above auroras, where an Alfvén wave is descending towards Earth and it's giving its energy to electrons. And it's been really difficult to capture that process with a satellite. You know, imagine a satellite flying through that, and it's hard to actually see exactly how the Alfvén wave is interacting with electrons. And so to test that kind of really detailed physics, the interaction of a wave with electrons, we turned to the laboratory. And this is a lab called the Large Plasma Device, or LAPD for short. It's a big experiment at UCLA, and it was made actually specifically for measuring how Alfvén waves interact, or how Alfvén waves behave in plasmas. And Liz has got a link to the Wikipedia page for the Large Plasma Device. So that's where we went to make Alfvén waves in the lab. And you can see it pictured here. This is actually a composite of a bunch of different pictures, because you can't back far enough away from it in the chamber, in the lab room. But it's about 20 meters long. So think of the scale of like a semi-trailer. And what's pictured here are a bunch of electromagnets. So these magnets, these coils, yellow and purple, create a magnetic field that goes left to right in this picture. And then inside of those electromagnets is a vacuum chamber. And in the vacuum chamber is actually where the plasma is created and the Alfvén waves are launched. So inside of all of this, we have an antenna. It vibrates at the right frequencies to kind of create, to make Alfvén waves. You have to introduce a magnetic disturbance. And so we can do that with an antenna, and that'll cause the magnetic disturbance to travel along through the plasma. And then what we did is we measured the response of electrons to those waves. And it's actually really kind of tricky to measure how electrons are responding, especially in lab plasmas. The ability to measure populations of electrons in lab plasmas is kind of an underdeveloped field. So we pursued that and developed a measurement and looked to see how electrons were responding to those Alfvén waves. So the general layout is here. We've got Alfvén waves launched from one end of the experiment, traveling down, and then a couple wavelengths away, we measured how the electrons were responding to that Alfvén wave. Okay, so before I show you results, and jumping over a couple years of kind of fine-tuning the experiment, I'm just gonna put an image in your mind of what we might expect to see. So if Alfvén waves give their energy to electrons, how do we think that might happen? And I want to give you the image of a surfer being accelerated on an ocean wave. I've actually never been surfing, but I've been told that the way to do it is not to just sit there on your surfboard. The way to do it is to paddle up to the right speed. And that's what you see this person here doing. The surfers that are not at the right speed just get passed by. They bob up and down and the wave passes them by. And so in the physics world, we'll call this resonant acceleration. The person or whatever is being accelerated by the wave has to have the right initial speed in order to be accelerated. And so that's been the prediction of how Alfvén waves would give their energy to electrons. So down below, I've got a video that's, I think it's exciting. My students think it's a little bit less exciting than surfing videos. But we've got a video showing how Alfvén waves might resonantly accelerate electrons, or how electrons might surf on Alfvén waves. So here is, there's two different electrons shown schematically in this very simple video. And there's no real difference between them except their initial speed. And so the red electron has the right initial speed to get picked up by the wave and push forward. And so that's a resonantly accelerated electron by this Alfvén wave in this really simple animation. So here's what we found in the lab. We found evidence that electrons do indeed surf on Alfvén waves. We found that they're accelerated by surfing on Alfvén waves. And here's the graph that kind of supported this. So on the vertical axis of this graph, what we're seeing is energy gained by electrons from Alfvén waves. And so if you look across the axis, what you'll notice is there's a whole range here where the energy gained by electrons is 0. And it turns out there's this whole range of velocities. So electrons at these velocities aren't gaining energy from the wave. But if we go over to a different range of velocities, we find, hey, wait a minute, these electrons are gaining energy from the wave. And it turns out that this is right near the initial, the speed of the wave itself. So electrons that are just a touch slower than the wave are the ones that get picked up and accelerated by the wave. But electrons that don't have that, have a different speed, that aren't going at the right speed to surf on the wave, those electrons are not accelerated. And so this is the first direct measurement showing that Alfvén waves can actually transfer energy to electrons in conditions that are relevant to the auroral acceleration region. Now, as a part of this, I had a paper come out about a year ago with this result, and this graph was one of the main features of that paper. But I was also asked to write a blog post to go along with the paper, kind of an explainer. And so if you scan this QR code, you should be able to like hold your smartphone right up to this and get to the website. If you scan this QR code, you can go to the blog post that explains the paper. And there's also a link to the paper itself in there too, if you want to go back to the original source. Okay, that's what I've got. Sorry, that went a little bit long, but I'll hand it over to Laura now.
Thank you so much.
Okay, my job as an educator is often to take exciting science and bring that to the classroom for my students. It's a pretty open playing field in terms of what school districts allow high school teachers to teach in their classroom. Some schools have a very rigorous and rigid, I want to say, the word I'm looking for is rigid curriculum, where they're adopting a curriculum and that's the only thing the teachers can speak to. And then on the other end of the spectrum, we have school districts that have general ideas. You should get some concepts through to your students, like this is a physics class, they should get your basic physics, or it's a biology class, there's basic biology information. And so I happen to work on more of that end of the spectrum, and generally in that end of the educational world. And so what I get to do is get exciting science and translate that into something that's digestible for my high school student audience. And that can range from freshman level all the way through seniors, from basic introductory type courses to advanced courses like AP level courses. So for this particular situation with Jim's research, I was contacted by Science Friday. They knew about me from being part of the education world, and I'm on social media tweeting about geoscience education. And so they said, hey, we have this great physics researcher. We think the two of you would work well together. And so Jim and I got partnered. So where I started was reading Jim's research. I actually got his papers and read through them. And that looked like you might imagine, where I had my highlighters and my pens, and I was Googling things and learning a lot of new words, and quickly beefing up my understanding of particle physics. And then Jim and I met, and I was able to ask him a lot of great questions. And as you can see, he does a great job of explaining these things. He's very clear. He has a lot of very usable examples. And so in talking with him, then what my brain starts to do is say, okay, in a classroom, what's the main goal here for students? What is the thing we want them to do? But I'm also putting that in a framework of how will the students approach that learning? So I don't know how familiar everyone here is with the changes that have been happening in education in the last 15 years. And I am going to share my screen. I didn't bring PowerPoints, but what I have are websites ready to go. So I'm going to share.
And I think just thank you so much. This is so interesting. I will also add that this is largely U.S. education systems, right? Yeah.
It is North America, though. I'm finding that a lot of places in Canada are starting to work with some of the ideas that are embedded here. So the next generation science standards are a series of educational standards that were developed, and they were developed based off of this document that was published in 2012 by the National Academy of Science. And I'll put this link in the chat for everybody, because you can read this free or download it. You can also purchase it, but it's available free. The Framework for K-12 Science Education is a document that guides how we should be creating educational science experiences in classrooms for students that are based off of what we know are best practices in science education, what we know actually occurs in classrooms because this document called upon teachers' expertise, and what we understand now cognitively about how the brain learns at different developmental stages. So this is a very well researched and very well put together document that really suggests that we need to be more explicit in teaching students the skills and thinking tools of science, and giving students more authentic experiences with science. And so much less of the, hey, everyone, we're going to do that LODIA experiment in biology, where we put the LODIA in the test tube and we count the bubbles and we confirm something we just read about in our textbook, which is photosynthesis will occur and they will absorb the carbon dioxide and spit out the oxygen. So we don't want to do what is called really a recipe anymore, knowing what the outcome should be. We want to approach that work from more of what we are calling a phenomena-driven idea. So a phenomena is really just anything that occurs, like aurora, or like an earthquake, or it really even could be, why does my cat go crazy when I put a box in the living room? So anything that takes place, and that the point of the phenomena is for students to investigate what's happening with the phenomena and come up with an explanation for why it's occurring. And so choosing good phenomena can be challenging. In this case, the phenomena was the aurora and the difference between discrete and diffuse aurora. What is causing these differences? Why do some have these very discrete zones? And so using this framework, I come to the next generation science standards, and these standards now break instruction into these 4 areas. There's science and engineering practices, which are things like asking questions, using models, designing experiments. There's cross-cutting concepts, which are thinking tools that scientists use, like looking for patterns in information or using scale and proportion. In this case with the Aurora, that things are taking place at the electron level that then result in something that is visible globally if you're in the right region. And so from micro scale to the macro scale, I'm looking at time, cause and effect. So those are the thinking tools that scientists are using. Then there's the content standards. So what is the content the students need to walk away with? And then in some cases, are they going to do engineering and design around this content? In the case of these Aurora, we weren't going to engineer or design anything. There's no problem to be solved. Like maybe for earthquakes, we might try to design an earthquake-proof building, or we might try to design homes that can withstand a hurricane. So in this case for the Aurora, we're not going to be focusing on designing something. But I'm coming and I'm thinking about these 3 main areas. Then we want to understand the physics that's taking place. We want to understand what are the practices that the scientists are doing to make sense of this, and what are the thinking tools. And so I developed, along with Jim, this resource that can be found on the Science Friday website. And again, I'll put a link in. And we are very proud that they have our surfing electron right there in the image. And so the way this was developed was to first give students the phenomena. What is this thing we're going to wonder about? And we want to develop curiosity in them to want to figure this out. So that's the first step. And so it begins with a brief introduction to Aurora. They can look at one. And we're asking them to do something that we do a lot in science. Think about what you're noticing and what are you wondering about? What observations are you making? What questions do you have? And in the case of this lesson, the students can keep track of it in a notebook, or there's a worksheet that we developed that teachers can print. And these are personal for the students. As a teacher, this is not something I'm going to grade them on. What I'm doing is building some interest and some curiosity, but allowing the students to do that in a very individual way. What they're going to do then is talk in their groups with each other, and they're going to share their observations. And so this allows them to broaden their own thinking by hearing from others, which is exactly what we know scientists do. We all notice something, we maybe share it, we share what we're thinking, we share questions, much like we're doing here today in this group. And then we're going to move forward from there. And so we ask a few other questions. We're guiding them a little bit. This is part of the online resource. In a classroom, an educator can choose to use prompts like this, or they can choose to ignore those prompts and guide the students in this discussion in their own way. So then we've come to this idea that these things are called auroras. They have a name, but we need to know a little bit more. Students are not going to develop the concept of electrons and Alfvén wave movement of those electrons on their own. And so our job is to guide them toward the new piece of information they need. And so the next part they need is to know what is an aurora. So they have some options here. There's a short reading that we developed, and you can link to it from there. It's written at a pretty basic level, and it's information that's pulled from a couple of different websites that's really just giving a little bit of background, so a little cultural background for students to know that people in different regions of the world have recognized Aurora. And so that also helps to build their cultural competency and helps to make students in the room of all backgrounds feel more comfortable and welcome. And then they're going to learn a little bit about them. And so the basics of what is it that's happening in an aurora, because today in this lesson, we're not here to figure that part out. We need to know that so they can read that. They can also watch a short video that covers similar information. And so here the students have choice about which way they want to go and beef up their little background on Aurora. Right. Next, we're asking them to build a model. And anybody who's done science knows that it's a pretty common practice, and we would call this an initial model, and that we develop those to clarify our thinking about what we think is taking place, and that these models also surface all of the things we don't know, which are frequently at this stage, many things. And so the students will be building these models. What they will do is build them individually. Then the students would be sharing with each other in their groups and gaining new ideas from one another. And so it's a very powerful learning technique that helps students to clarify their own thinking and grow from the thinking of others, and also learn to value the thinking of others, that everyone's brain and everyone's background experience will be different. And so everyone's model will be a bit different, and that we all have a really important piece of information to add. And so we'll frequently go from this individual small group and then whole classroom behavior to help build and create that value for everyone's perspective. So they're making their model. It's a visual model, so they're drawing it on paper. And then we're going to be talking about them, and we're going to be having these group discussions. Right. Now that they have a model, then what we're going to do is compare two different models. And so this is where we do exactly what Jim did for us in the opening, is we're going to observe, here are two different kinds of aurora. What types of things are we noticing? What types of things are we wondering? And then the students are going to have conversations in their small groups and have conversations with the class. And the teacher's job will be to bring up all of these things that the students are noticing and then gently guide them toward focusing on the discrete aurora. Then we're going to move the students into some data. So we have questions about this. What's causing this discrete aurora? Why does this one come in such a kind of a narrow band? And why is the other one just everywhere? So let's look at some data. We're going to go gather some new knowledge. If we put the students just out on the internet and we said, Google it, they will quickly get lost in the weeds. And so part of our job as educators is to say, I have found some resources to help you. And so what we did for this portion was we took a look at these satellites, and then Jim and I took his very complex data set and we have simplified some of that information. So the students are looking at these and getting an idea about where these two satellites are located, much like we did earlier in Jim's presentation. And they're also looking at this information. Now, we're not telling them anything at this point. We're just saying, hey, look, here's where the polar is, here's where the fast is. What do you notice? And we're going to allow the students to figure this out. It should be pretty obvious for most kids. But one of the powerful learning techniques that we can use in a class is, instead of telling students, we can allow them to figure it out. And it takes a little bit longer, but that information will sink more deeply into their memory because they were the ones that figured it out. So they're going to notice what we noticed. There's a difference, and we're going to now add to our model. So we've developed a model. Let's put these satellites on. We can add these numbers. What kinds of new questions do we have? And there'll be a variety, but inevitably at least one student is going to say, well, why are they different? What happened? Why are these numbers not the same? So that's great, because what that does is that's our launching point into what has happened to the energy. That's when we start bringing up, how can we move particles, which is a kind of a basic physics concept for high school students. And so this is good because we want them to develop this idea. What are some ways we can move things? So we also present a video of surfers, and we are walking the students into recognizing exactly what it was that Jim was sharing with us, right? Which surfers are catching waves here and which don't? What is different? And in this video, which is a little bit longer, hopefully the students will start to make the observation that only some of the surfers get the wave, and they're going to start to recognize they have to be moving and moving at the right speed. You can't just be moving, you can't be sitting still. And so this allows students to make observations. They'll share their thinking in their groups. there'll be a classroom conversation where we develop this idea. And if my students aren't coming in the direction that I'm hoping for, then my job is to listen to them and then maybe focus them by asking questions that will help kind of guide their thinking in that direction. So, okay, if we think maybe the waves are moving those electrons, how do we know? What is a way that we could confirm that? What would we expect to see? So then we're sharing that when they're coming from the sun, the electrons have a random distribution. And so let's model that. We're going to make some histograms. And so this is where Jim and I worked to come up with some more simplified data, because the data that he really works with is very complex. And because our goal is for the students to learn how to use the tool of a histogram and to learn how to interpret the information, the hurdle of trying to understand that real in-depth data is probably too large. And in a high school classroom, the amount of time I would need to develop their understanding is very likely more time than I will have for that year. And so this is where sometimes we take ideas and we simplify them. And that's what we've done here. So the students are going to develop some histograms, and they're going to see some distributions. Okay. They're going to then be looking at those data sets, and what they're going to start to recognize is that these data sets are going to develop very similarly to this movement that we're seeing here. And so we're now giving them our animations, where we're going to see that if the wave is moving these electrons, right, we can start to see there's a difference in the distribution for those that are getting grabbed and moved forward by the wave. So the distribution of this information should be different. And that is, in fact, right, what occurs. And so we're allowing the students, again, to sort of discover this on their own. So then we're going to come back to their model, right? They're going to come back, they're going to add any new ideas. What do they think might be taking place? What might be occurring? And then, of course, we are going to be wondering, so what is accelerating them? Is it something? Well, it turns out we have this information for Alfvén waves, and we're going to present them with this graphical data, this visual data, and we're going to allow them to look and see, right? Here is where we're going to see Aurora. Here's where we see Alfvén waves. Tell us what your thinking is, right? What is happening? And based on what we know so far, what do you think makes sense? And then they're going to add them to their model and develop a consensus model. So at this point, then the class will start to come together, and we'll start from scratch, and we'll develop a whole class model that has all of the things that we think are taking place, so that they can draw the conclusion that it is, in fact, these Alfvén waves that are doing this movement. That's the cause, and this is why we get these discrete aurora. And so this is the basic pattern, and really the purpose is that our students are doing the investigating themselves, even though it's, I would call it like a contained investigation. For physics of this caliber, I can't take them to the laboratories in UCLA, and we can't do some of the more sophisticated mathematical work or computer modeling that might help them. But what we can do is give them a more simplified version and the opportunity to work in teams, to share their observations with one another, and value the contributions of their group members, and use modeling to develop this idea that this is what is taking place. And so it's a really good example of how we're trying to do science teaching in the K-12 world now, guiding students in the journey, providing them with resources so that they can get the information they need, but giving them a structured environment to make sense of it. And so,
thank you so much. It's awesome to hear from teachers about how they interpret this complex science, and for the classroom and for the way that kids learn. I really, really appreciate that. That's a very hard job. So there are definitely some questions and conversation in the chat here. I wonder if there's Have you actually had a lot of other teachers try this resource since it was so, widely published on Science Friday, or have you had much good feedback from that?
I actually haven't had the chance to speak to anyone who's used it before. I think part of that is we've still been in a pandemic year, so a lot of high school teachers are still just, our heads are barely above water. And I don't know if there's a measurement on the Science Friday website for them to look and see how many people have accessed it and used it. It is one that I will be sharing with my own colleagues this year. I was a little hesitant to put anything new in their direction last year, but as we get ready to start fresh, there are 2 high schools in my district, and they're working very hard to try to change up their very traditional way of teaching physics. And so this is one that I'm going to be sending in their direction, and definitely asking them for their feedback. So
Very
I'm
cool.
always curious to hear, what is it like out in the wild?
Mm-hmm. Does anyone want to jump in with a question? Jeremy, you had a good question.
Yeah, I'm just thinking back to when I'm a student, and there's this, I don't know, it's like taking the very first piece of cake out of the cake pan when you take it out of the oven. It's like, it's the hardest one to get out, because you have no place to start. And it's like that with, I think, curiosity and inquiry. And I was wondering how we build that very first spark of inquiry, or how do you train that, sort of like a muscle? I can see that it picks up speed as you have a structure for asking questions upon questions and getting the responses. But do you find that there's some people that just have a skill set for knowing their curiosity and starting things?
My experience is that it starts with the phenomena that you choose. So the thing that you're putting in front of students to observe and wonder about is really that's going to be the starting point. Aurora are easy because they are cool. And I've never seen a student not think it was cool. Even the most jaded, I am not interested in class student gets excited about Aurora. So Aurora is a great phenomenon because everybody's like, wow, that's beautiful. I love the colors. What is that? There's so many kinds of questions and kinds of excitement that extend from that's a really easy one. Other than that, part of what's challenging as an educator is you have to know your students. And that means you have to know like your community, and how your community's different maybe from other communities. My students, we live in the Central Valley of Turlock, and compared to communities in larger cities like the Bay Area or New York, we aren't as well educated or wealthy. And many of my students have never been to the ocean and don't know much about the natural world around them. And so for my students, if I'm going to say, there's this thing called ocean acidification, and it's really terrible, they have no interest. My students don't really relate to the ocean. They've heard of it, but it's not personal to them. And so developing your phenomena for a sense of place for your students, that it connects with who they are and what is important to them, where they are, is really important. Sometimes that's where they are as teenagers, because I teach high school students. So sometimes that's really connecting with their sense of social justice. They're very just people. It's always impressive to me. Students are just, and they want the world to be fair and right. Or maybe it's connecting with things that they think are interesting, like music or cars. It really varies. Sometimes it's helping them to recognize that actually there's this neat thing and it happens right where you live. I did a unit with my students last year on some fossils. We have south of us by about 35 minutes, a Pleistocene fossil location that it's one of the most complete and diverse representations of Pleistocene fauna in the world. But where I live is flat and it's almond farms and it's boring. And if you're a teenager, it's really boring and nothing ever happens here. And so they have no idea about that. And so what I started with was, what do you think it was like here in Turlock 2 million years ago? what do you think this place might have been like? That's how we started. And so the students could put all their own thoughts together. And then we had this that whole day, we took a whole day for that. We just had a class conversation. And so students tried to understand how long ago 2 million years was, and they shared ideas. And some of them said there were probably cave people and mammoths. And so some of the information turned out to be accurate, and a lot of it wasn't. But it was our starting point, and they got really interested in it. Suddenly they were really curious. What was it? Were there houses here? Was Target here? They don't really know. And so there's so many ways to do it, but a huge part of it is knowing your students and just trying to pull that out of them, like meet them where they're at. I can also tell you, there've been plenty of times I've done this and it's been a fail. We did a unit also this last year trying to look at how urban ecology is driving evolution. And the initial few things we had students look at were kind of interesting, and then it just fizzled. Like within a week, they were done. They had no interest whatsoever. And so I just stopped and I shifted gears because it wasn't going to work. If they're not interested, it's not going to work. And so that's part of it. Sometimes you fail and you start over.
Yeah, in the Aurora field, it's, I think, definitely something that we would love to have more examples of how to succeed using auroras as the phenomena of interest, because especially many people don't have too much familiarity with it, and or aren't approaching it in a way that piques their interest maybe. Yeah, I also want to, well, I wonder if you have anything else to say about that with respect to auroras. Tips for us. The beauty is a great motivator, but yeah.
I mean, things I've seen done, some students are more interested in art. So maybe you start with the art. Maybe you ask students to draw, or you bring in different artistic media and say, you know, here's this really cool thing. Like today we're going to create some, let's just create ours. And so maybe you start by connecting with their sense of beauty and art. Maybe you live in a place where a particular culture has stories about Aurora. And so maybe you start there, you get some of that information and you share them and you have them read them. And then maybe what you could do is compare those with another culture. Hey, you know, our region, this group of people, they have these really great, beautiful stories about Aurora. What happens if we go down to like New Zealand or Australia? What do people from those regions have to say? Let's compare the stories. What's the same and what's different? And you sort of let the students guide you a bit. Listen to what they're sharing with you and what they think are interesting. In terms of diving deeper into, you know, the more sophisticated physics, I mean, sometimes we have things we have to learn in a class, which is, you know, not as much fun in terms of just allowing it to be student driven. But if you can ask the students the questions they have, and if there's a way to explore those and layer those important concepts in, I think that's really valuable too. It depends on the class, right? If it's an introductory level class, I would always say in any introductory level course, the most important thing is that you really want to educate and inspire the students who aren't going to go on to dig deeper into physics or any science, because this might be the only science that these students are getting. This is it. And so they need to really walk away with understanding how science is done. I think a good sense of the process and a good sense of how to read and understand scientific literature is important, because look at the world today with COVID. How many people say I've done my research, but I'm pretty sure very few of them have read scientific research papers on COVID, even though it's abundantly available. And that's because those papers are dense and intimidating. But when people have the experience of seeing them, they're not as intimidated. For students who are going to go on, right, you know, these students are majoring in physics or majoring in astrophysics or something of that nature. There's always going to be a certain amount of things you just need to know, because it's easier to work with that information when it's in your working memory, if it's memorized. And I think that's okay to share with students as well. In more advanced courses, I tell my AP students have to memorize a lot, but I make it clear why. It's not because this is what you need to do. But because if you have all of these ideas memorized, now you can grab them more quickly. And so our real goal is to then be making connections and explaining things. So I think there's a fair amount of compromise that goes in there, depending on your audience and your course and your purpose.
Yeah, thank you so much. That's really inspiring me, definitely, and I'm sure others. We are kind of at time here. I understand if anybody has to drop off. I definitely have another question or two for you guys, if you're able to stay. And one is about what Alphanic Aurora looks like, because I think we have all kinds of really amazing images, like Donna has some images in her background that are beautiful arcs there. And yeah, how do we know if it's an Alphanic Aurora? Can we tell from just the image, specifically, scientifically? That's one thing I'm curious about. And I appreciate the paper. I haven't yet looked at it. So does Jim have any answer for that? Or
Yeah,
is that something you guys looked at together?
As far as I know, there's no optical signature of an Alphanic Aurora. People have in the past looked at, so what are known about Alfvén waves are typical wavelengths and typical frequencies. And so then you can analyze like all sky imager data and look to see, are the variations in the intensity of auroras, do those map to typical Alfvén wave frequencies? And the answer is mixed, like many times when you do a study like that. Sometimes yes, sometimes no. But of course, the picture of Alfvén waves coming down towards Earth is more complicated than what I was, but there's more to it than what I was saying in my brief presentation. There can be reflections and waves going both ways and standing waves and actually kind of like static structures that are attributed to auroras. So you might not get that variation at the frequency of the wave because of all this kind of complicated reflections and standing waves. So all of that is to say, people have looked, and as far as I know, the answer is basically no, there is no obvious optical signature. Oop, Liz, you're muted.
Sorry. There is a lot of like flickering when you see like the really high speed motions. That's a possible signature, but yeah, I'm gonna think more about that as well. And you both are welcome to come back if you want to join more of this group. We also are reading a classic article about auroral forms by T. Neil Davis. Some of the first discussions of or definitions, a review article about discrete and diffuse aurora, and how that kind of looking at those signatures and the different curls and folds and what the physics is there. So yeah, all right. We have probably a few more minutes for other questions. Thank you. Sorry to bombard you with my questions. I'm sure that others have a lot of great questions here.
Liz, can I kind of piggyback off of your question?
Sure.
Do we have a decent understanding of how Alfvén waves contribute to the energy budget of this region? Because I know that's really difficult to disentangle from other processes like reconnection. For context, I'm coming at you from a solar physics background and I do solar magnetic reconnection. So we have kind of the same issue. We're trying to constantly explain the energy budget of the solar atmosphere, be it waves, reconnection, etc. Is there, have y'all been better at that than us? Or are we kind of in the same boat?
Yeah, this is, so that there has been some work in recent years to kind of go back to the fast data and the polar data and try to reconstruct an energy budget. The specifics of this are kind of escaping me. Remember, I'm a lab experimentalist. But my recollection is that several papers kind of arrived at conclusion that the amount of energy coming in from Alfvén waves is, if you just do a global average over space and time, the amount of energy coming in from Alfvén waves is sufficient to cause about 1/3 of the auroral light that's produced. Now, that's not saying that all of the energy coming from Alfvén waves is actually converted into auroral light. So that conversion fraction is certainly something less than 1. But if you assume it's 1, you could get about 1/3 of the auroral light. So it's not the majority, but it's also not insignificant, right? So in an effort to understand how the magnetosphere is sending energy down towards Earth and coupling to the ionosphere, that's a piece of the pie that you want to try to understand.
Yeah, that's actually that's really significant, I would say. Cool, thank you.
Yeah, you're welcome.
Yeah, I think I'm also definitely interested in some of these papers by Andreas Keiling about basically, it sounds like what he's defining as the dynamics, the Alphanic auroral oval, and something kind of new and probably not as well defined or investigated as the traditional auroral oval, but sounds interesting to delve into and relevant for your question, Becca, as well as the solar questions too. So all right, any more questions, folks that want to try these resources? I really appreciate you stepping us through the motivation, Laura, and how that works. I don't know, Jim, if you are in the classroom at all in your, if you do anything with high schools or adapt this for more colleges, or do you have any additional kind of thoughts on the teaching physics with Aurora?
I haven't really had an opportunity to bring a lot of this into the classroom. I tend to teach kind of the first half of the curriculum here at Wheaton College, so up through kind of a modern physics type course. So far has been my focus. Yeah, so I'll leave it at what Laura said, because that was what she said was great.
To explain what you said, you are not teaching electricity and magnetism yet. That's what you mean.
Not regularly. Yeah, I've taught it once.
Yeah. Okay. Cool. But yeah, there's very different, Newtonian and physics and all kinds of other starting points. So, what else? Other questions? So much here to delve into. So. Do you have any new plasma experiments that you are working on? That is one question. And also, when you were speaking earlier, Jim, I was reminded of the plasma formulary book, which is this book about this high. Jim has his accessible here. I should have mine accessible. Yeah, if any of you all want a really nerdy book, show them some of the equations, but this book is not a textbook. It's mostly not gonna help you unless you've studied all of the physics, but there's also free versions online. But if you want to really talk like a plasma physicist and throw out all the terms and look at some of the equations, there's this mini little book called the Plasma Formulary that everybody has, and apparently you have many copies of it for persuading students to study physics, I'm guessing. So yeah. But yeah, my question was, what did I just ask you? Oh, your next experiment, the LAPD.
Yeah. So I'm, my next work is likely not going to include LAPD, although I'm kind of staying in this realm of lab experiments that have relevance to space plasma. And as I was mentioning before, I'm guessing there's some people in the room that have worked with spacecraft data. In space, you can measure particle distributions that are beautiful, and I'm jealous of them because there's not a density of plasma that can create arcing inside of your diagnostic, and also the spacecraft is small compared to typical scales of the plasma. In the lab, it's a lot harder. And so I've worked on developing measurements of electron distributions, which is even harder still than measuring ion distributions. With ion distributions, at least you have some atomic transitions that you can take advantage of in your effort to measure distributions. So I'm trying to go after this kind of very niche field of looking at electron distributions in the lab, and specifically how they might respond in scenarios that are relevant to space. The next thing I'd like to do, I'm in the middle of writing a proposal that's due in 13 days, where I'd like to look at how something called Whistler mode waves interact with electrons in a region of space called the radiation belts. And so this might be more related to the diffuse auroras.
Yeah, definitely. There's good connections between the lab plasmas and the experiments there. So I've worked on both areas myself, so it's all good, familiar stuff. And I know how hard it is as well. So great. All right. Well, I appreciate Laura's suggestion that we need a cartoon guide to the plasma formulary. So if any of you all have some extra time, that would be a worthy effort and much appreciated. So I think we'll quit there for today. Thank you all very much. And we'll see you next month. I don't recall exactly what next